Hi everyone, Dr. Burns here with our next lesson, continuing on with our discussion of chemical reactions, energy, heat, and work. So let's talk about reactions that are carried out at constant pressure. Pressure volume work, or PV work, is done when there is a volume change under constant pressure. So this is like a piston in your car engine that moves up and down when the engine is running. We define work in our previous lesson as just W as the work being done on or by the system, but we can determine it mathematically through the relationship of work is equal to negative P delta V, where P is the external opposing pressure, so the pressure that's outside of the system, and delta V is the change in volume of the container. So again, delta V, that's a state function. So we know that delta V is equal to V final minus V initial. So if we know the change in the volume and we know the opposing pressure, then we can find the work that's being done to cause that change in the volume. So let's look at a practice problem where we can do just that. Here we want to determine the work done in joules when a sample of gas expands from 552 milliliters to 891 milliliters at constant temperature against a constant pressure of 1.25 atms. Now, an important note here is that we want our answer for work to be in joules. As we discussed in our previous lessons, the work unit relates to energy, and the energy unit is joules. But what we're given here with pressure and volume is pressure is in atms, and change in volume is in liters, or in this case, milliliters. So we need a conversion factor to go between a pressure volume unit and a work energy unit. So that's what this conversion factor is down here. When we solve this problem and take our pressure and multiply it by our change in volume, we'll then use that conversion factor to convert the value from liters times atms to joules. So because that conversion factor is in a unit of liters and atms, we need to make sure that our volume and our pressure are in the correct units. Our pressure is given to us as 1.25 atms, so that's in the correct unit. But our volume units are in milliliters, so we are going to have to convert those. So let's look at this problem. We know pressure, P is 1.25 atm. And for delta V, we know that it's going to be the final 891 milliliters minus the initial 552 milliliters. Now, you could do this two ways. You could take the difference of those two values now and then convert that difference into liters, or you can convert those two volumes into liters and then take the difference. Either way that you do it is perfectly fine. You'll get the same answer. You just have to make sure that your unit of delta V is in liters so that we can use it for our conversion factor later. So let's take 891 on our calculators. Feel free to get your calculator out and do these calculations with me so you're comfortable doing them. And we're going to subtract off 552. That gives us a delta V of 339 milliliters. We will then convert that milliliters to liters because we know that in 1 liter there's 1,000 milliliters. So we'll divide that by 1,000 to get 0.339 liters. So we're going to use this pressure and this volume, change in volume, to find the work. So we get work is equal to negative P delta V. So negative 1.25 ATM times delta V, which is 0.339 liters. So we'll take that 0.339, we'll multiply it by negative 1.25, and we'll get that work is equal to negative 0.42375 ATM times liters. Now it's very important when you're calculating delta V to make sure you are getting the final and the initial correct, because that's what's going to determine our sign for W. Okay, so the work equation already has a negative sign on it, but if we were instead not expanding but decreasing our volume, this value would then also be negative, which would change the sign of the work. So you need to make sure that you are doing your final minus your initial when doing your delta V, because that's what's determining the sign of your work. So from this, we know that our work is negative, and it's currently in units of ATMs times liters. So now we want to use our conversion factor up here to convert from ATM liters to joules. So we'll put ATM liters on the bottom, just one of those, and we'll put 101.3 joules on the top. So we'll take that negative 0.42375 and we'll multiply it by 101.3, and we get out negative 42.9 joules of work. And make sure you maintain that negative throughout, because as we saw in our previous lesson, the sign of W matters because it will tell us if we're doing work on the system or by the system. Let's do another example. Try this one independently. A gas expands in volume from 26.7 to 119.3 milliliters at constant temperature. Calculate the work done in joules if the gas expands against a pressure of 3.5 ATMs and against a constant pressure of 10.1 ATMs. So what we're doing in this problem is we're taking this volume change and we're looking at it compared to two different p-values. So we're going to find two different values of work. And what we're going to see is that different pressures will require different amounts of work to make the same volume change. And that's because the pressure is external and it's forcing against that volume change, against that piston moving up and down. So we'll see, do we need more pressure to have more work or less pressure to have more work? So let's calculate that now. Pause your video and solve for work for both of these problems. I will put our conversion factor for joules to ATMs, or liters times ATMs to joules, on the screen for you. Since our volume change for both of these calculations is going to be the same, let's go ahead and calculate that now. Delta V is equal to 119.3 minus 26.7. And those are both in milliliters. So the change is 92.6 milliliters. We just want to convert that to liters, and we get 0.0926 liters. So that's the delta V that we're going to use in both of our calculations. So the first one, our pressure is 3.5 ATMs. So W is equal to negative 3.5 times 0.0926 liters. So negative 3.5 times 0.0926. That gives us a work value of negative 0.3241, and that's liters times ATM. We'll then use our conversion factor and multiply by 101.3 joules to cancel out our liters ATMs. So we'll take that and multiply by 101.3, maintaining that negative sign, so we get negative 32.83. And with sig figs, we'll call that 32.8 joules. Actually, that's to be 33 joules with sig figs. Sorry, there's 2 sig figs in my pressure. Changes for the next one. So 33 joules. There we go. Sig figs, 2 sig figs there. That's our answer for our first pressure. Now with our second pressure, we're going to do the same thing. Instead, we're just going to plug in that 10.1 ATM and multiply it by that same volume change. So we get negative 10.1 times 0.0926, which gives us a work value of negative 0.93526 liters times ATM. Again, I'll multiply by 101.3 in order to get units of joules and cancel out my liters ATMs. So we'll multiply that by 101.3 and we get negative 94.7 joules. This one has 3 sig figs because of the 10.1. So we can see that if we increase our pressure, we need to do more work to have the same amount of volume change as a lower pressure. So when we had the lower pressure of 3.5 ATMs, we only needed to do negative 33 joules worth of work. Whereas when we increased the pressure to 10.1, we had to do 94.7 joules worth of work. So with pressure volume work, okay, this is done when there is a volume change and the pressure is constant. Okay, now we can plug that new work value, that new work expression in to our internal energy equation. Okay, we learned in our previous lessons that delta U is equal to Q plus W, heat plus work. But now we have a new definition of work, which if we didn't have the work value, okay, if we didn't have that experimental value, but we had the pressure and we knew how much the volume changed by, we could find the work. So we can plug that in for W as we see here. Okay, we're just plugging this negative P delta V in there. Okay, and we get delta U is equal to Q minus P delta V. So it's just a new expression for our internal energy equation. Now, when a change occurs at a constant volume, we see that delta V is equal to 0, and no work can be done. So if we say that delta V is 0, this whole term goes away, because if we multiply P by 0, the whole thing becomes 0. So we get that Q is equal to the internal energy. The heat is equal to the internal energy. So if there's no volume change, then we get heat is equal to internal energy. So when we're working with this equation, we are always going to be working with constant pressure and a volume change. So here's our equation again for our internal energy is relating to Q and P delta V work. And what we're going to do is we're just going to rearrange that equation because experimentally it's easier to determine these values, pressure and volume, we can easily find, as well as the total energy of the entire system, whereas measuring heat is not as easy to do. We'll learn about how we're going to measure heat later in our lesson, but for right now, for what we know about these systems right now, determining heat experimentally is not as easy. So if we want to find that Q value, it's actually easier to take the internal energy and the work, the PV work, into account in order to find the Q value. So let's practice that. Just practice using this equation here. A gas expands and does PV work on the surroundings equal to 325 joules. At the same time, it absorbs 127 joules worth of heat from the surroundings. So we want to calculate the change in energy of the gas. So while we have many different expressions that we could use, such as delta U equals Q minus P delta V, Q is equal to delta U plus P delta V, delta U is equal to Q plus W, they're all related to each other. So no matter which equation you use, you'll find the same answer. So let's look at the language of this problem. This one says, does PV work on the surroundings, which is equal to 325 joules. Since we're already in units of joules, we know that that is just our work value. So work is equal to negative P delta V, okay? Now, unlike our previous problems in our previous lesson, our sign for work is going to be dictated strictly by the number that is given in the problem, okay? So, and that's because it's saying I did PV work and the sign is already accounted for in the PV work by that negative and in our new equation of delta U. If you were to just think of this as just work as W using delta U is equal to Q plus W, the wording of the problem would then make you have this be negative 325, which would also do the same thing as the negative here. So it works out, okay? So when you're looking at these problems, when it says it's doing PV work, you don't have to look at the language to show that it is positive or negative. It's dictated by the problem already. The one we do have to worry about is the amount of heat in the problem. So it says that it absorbs heat, which would be Q is positive. Okay, so if we know PV work, if the problem specifically says PV work, then don't consult the language. If it doesn't say PV work, then you need to look at the chart for the language. So we know that Q is going to be positive. So Q is positive. Okay, so now we could just plug everything in. Delta U is equal to Q, 127, minus, because that minus sign in our equation already accounted for the signs, and that's going to be 325 joules. Okay, so we're just going to take 127 minus 325, and we get out a delta U of negative 198. So up to this point, we've seen many expressions that we could use to solve for heat, work, and internal energy. Those have all been kind of summarized in our past lesson as well as the beginning of this lesson, but they all relate to each other in some way. So just make sure you know how to properly use all of those equations when you're going through your ALEKS homeworks. The next thing we want to start discussing is some thermodynamic properties. We're going to discuss these over the next few chapters, but the first one that we're going to talk about is enthalpy and enthalpy changes. So the thermodynamic function of a system is called enthalpy, which we denote by the letter H. And this is defined by the equation H, enthalpy. I'll label these. So H is enthalpy. U is internal energy, P is pressure and V is volume. So enthalpy equals the internal energy plus the pressure times the volume. Since enthalpy is a type of energy, it is a state function. Therefore, the change in enthalpy, we just add those deltas. So we add delta H is equal to delta U plus delta P times delta V. Now we know that when we have PV and a delta in front of them, the only one we care about, if we were to put this in, we get two options, delta P, delta V. But we know that we're going to be doing things at constant pressure. So there will never be a pressure or a change in pressure. So this breaks down to then P delta V, which is our work expression. So that's what we plug in here. So if the pressure is constant, the enthalpy change is equal to the change in internal energy plus our PV work, P delta V. We know that Q at constant pressure is equal to U plus P delta V. And we now know that delta H, the change in enthalpy, is also equal to U plus P delta V. Therefore, Q, the heat at constant pressure, is equal to the change in enthalpy. This also means that enthalpy has units of joules. Specifically, we're going to see enthalpy with units of kilojoules. Those are its constant units, are going to be kilojoules, which we'll discuss as we move forward. So, enthalpy is defined as the internal energy plus the pressure times the volume, and since it's a state function, we can simplify or change that equation to say that the change in the enthalpy is equal to the change in internal energy plus PV work. We know that heat at constant pressure is also equal to the change in internal energy plus PV work, and therefore the heat at constant pressure is equal to the enthalpy. So let's practice using that equation. The enthalpy of a mixture of gaseous reactants decreases, we'll make that known, decreases by 192 kilojoules during a chemical reaction carried out at constant pressure. It was determined that 146 kilojoules of work is done on the mixture during the reaction. Calculate the change in energy in joules of the gas mixture. So, because our enthalpy equation uses PV work, we don't need to do anything with the sign of the work in this problem. Okay, so we just have to plug everything in, make sure they're in the same units, and then we can solve. So we know that delta H decreases by 192 kilojoules, meaning that its sign is negative. We know that P delta V is our work, and that was equal to 146 kilojoules. And again, since it's PV work, we don't need to worry about the sign. And finally, delta U is what we are looking for. So we just have to plug in our values because they are both currently in units of kilojoules, which is an acceptable unit for enthalpy and energies. So we are going to take that negative 192 kilojoules equals delta U, which we don't know, plus 146 kilojoules. So we'll take that negative 192 and we'll subtract off our 146, and we get a delta U that is equal to negative 338 kilojoules. Our problem asks for the energy now in joules, so our final step is going to be converting kilojoules to joules. I know that in 1 kilojoule, there's 1,000 joules. We've been doing that a lot in these lessons. So we'll just take that negative 338 and we'll multiply it by 1,000. And with sig figs and scientific notation, we'll get negative 3.38 times 10 to the 5th joules. And there's our final answer. So that is our value for delta U in this expression. So the enthalpy of reaction, so delta H, is the difference between the enthalpies of the products and the enthalpies of the reactants. So this is just like what we were talking about previously, where delta means final minus initial. The products are the final portion of a reaction, and the reactants are the initial. So when we're talking specifically about reactions, instead of saying final minus initial, we'll start saying products minus reactants, the final part of the reaction minus the initial part of the reaction. Most reactions in the lab occur at constant pressure, which is why we only care about P delta V when we're talking about work. Therefore, the heat exchanged in a chemical reaction in the lab is equal to the change in enthalpy. So we can now relate our sign of delta H to an endothermic or exothermic reaction, just like we did in our previous lesson. So if delta H is positive, then it's an endothermic reaction or an endothermic process. If delta H is negative, then it's an exothermic process or an exothermic reaction. It's giving off heat, like an explosion. So we're going to start looking at these chemical reactions and chemical equations now with thermochemical values attached to them. So here we have the changing of water to water from a solid to a liquid. So ice to liquid water. Okay, so if I put some ice in a glass and just let it sit, okay, so now we've all seen chemical reactions that look like this. Okay, we go from a product or a reactant to a product. We show our states. We make sure it's balanced. But what we're adding to this now is our thermochemical information. So for this equation, for this reaction of ice melting, the change in enthalpy, the delta H, is positive 6.01 kilojoules per mole. So this is a thermochemical equation. When we're looking at these thermochemical equations, we have to answer a few questions about it. We first have to consider, what is the system? Well, we define the system as the reaction or the portion of interest where we are measuring the heat. So in this, what is the system? Well, that would be the water, the H2O. Before, when it's a solid and when it's a liquid, what is going to be either taking in the heat or expelling the heat? So the system is the water. What are the surroundings? Well, the surroundings is everything else around it. And finally, is this reaction endothermic or exothermic? Well, we just stated on our previous slide that if delta H is positive, this is an endothermic reaction. And we defined endothermic as heat being transferred from the surroundings to the system. Well, when we're melting ice, we want that ice to warm up, so we need to take heat into our system, to the water, from the surroundings, which is everything else around it. Okay, so heat is being absorbed by the system from the surroundings, and specifically the amount that it takes to do that is 6.01 kilojoules per mole. So This is how we think about thermochemical equations. We need to think about the system, the surroundings, and what the sign of that thermochemical variable, in this case enthalpy, is telling us about that specific reaction. So let's look at another one. Here we're looking at methane reacting with oxygen gas, creating carbon dioxide and water. This is a combustion reaction. If you remember from Gen Chem 1, this is a combustion reaction. We're taking a carbon-containing compound, reacting it with oxygen gas, and creating carbon dioxide and water. So we have our balanced chemical equation here, as well as our value for enthalpy, which in this case is negative 890.4 kilojoules per mole. So let's define our system. What is the system? Well, it's the methane and the oxygen. Because that is what is reacting. That's what we're using to either give off heat or take in heat in order to react and create our products. What are the surroundings? Everything else. And is this endothermic or exothermic? Well, if this is a combustion reaction, we know that we're giving off energy, right? If we think of something combusting or think of something exploding, exploding means exothermic, which relates to our delta H, because we said delta H, when it's negative, is an exothermic reaction. So a negative delta H is exothermic. A combustion reaction is an explosion of a carbon-containing molecule reacting with oxygen, giving off energy. Okay, so the system, the methane and the oxygen are reacting. They're giving off energy in the form of heat to the surroundings. They're exploding. There's fire, there's flames, there's heat. Okay, so this is an exothermic reaction. Now, enthalpy is an extensive property. We haven't talked about extensive properties in a long time. We talked about it, let's see, in General Chemistry 1, probably Chapter 1, around there. Yeah, I think it's Chapter 1. But just to reiterate, to review, extensive properties are dependent on the amount of matter involved. Okay, so let's look at the reaction of water going from a liquid to a gas now. So we're evaporating water. So when I evaporate water, that requires a delta H of 44 kilojoules per mole. Now if I double the amount of that water, it's going to take more energy to complete that reaction because there's now more matter involved in the reaction overall. So if I double the amount of matter and now have 2 moles of water turning from a liquid to 2 moles of gas, okay, what's going to happen to the enthalpy is it's also going to double, okay? So it's an extensive property, meaning it's dependent on the amount of matter involved. So however you change the chemical equation, you should also change the enthalpy. These thermochemical equations, our delta H has a unit first of kilojoules, but now we're adding on a per mole. Okay, that per mole means per mole of reaction. So for every 1 mole of this reaction overall, it requires negative 802 kilojoules of energy in order to do that. Now, because this is per mole of the total reaction, we can calculate the enthalpy change for the number of moles of the reactants and the products in the balanced reaction. So not only the reactants and products. Okay, so for this reaction, for the reaction of methane, it's negative 802.4 kilojoules per mole of reaction. And in that one reaction, there's 1 mole of methane, CH4. This is going to be 802 kilojoules released per 2 moles of oxygen. or 1 mole of CO2, or 2 moles of H2O. A good way I like to show this is using a classic mole to mole ratio, only the mole to mole ratio is a little bit different than what we've seen in the past. So if I take this negative 802.4, this is going to be kilojoules per mole of reaction. Okay, my mole ratio I can now set up. In 1 mole of reaction, I have 2 moles of O2. Or you can write this as, for every 1 mole of reaction, I have 2 mole, or let's say 1 mole of CH4. So that's how we're able to convert it from the total moles of reaction overall to individual reactants or products. So we could technically rewrite this now as negative 802.4 kilojoules per 2 moles of O2. Okay, moles of reaction ends up canceling. Now, you could keep this as 802.4 over 2 moles of oxygen, okay? Sometimes that's just easier. You'll see in our practice problems that we're going to do that maybe that's the easier way to do it. Or you could do that division and say for every 1 mole of oxygen, it's 401.2 kilojoules per mole of O2. You would have to specify that that is for moles of O2 now and not for the full reaction. Okay, so that's how we can use our mole to mole ratios to show that for these thermochemical equations, the mole that we're talking about here is for the whole reaction, or we can substitute in our coefficients from out in front of our reactants and our products. Okay, so let's do a few practice problems with this. So, given the thermochemical equation for photosynthesis, okay, we're given it here, water and carbon dioxide create glucose and oxygen. Calculate the solar energy required, so here's our energy. Calculate the delta H value, kilojoules, okay, required to produce 75 grams of, this should be C6. I don't know if that's a typo in your lecture notes as well, but if it is, change that to C6H12O6. Sorry about that. Okay, so essentially what this problem is asking us to do is take our mass of glucose, C6H12O6, and somehow get it to a value of kilojoules. Okay, that is the goal, but we can't go directly from grams to kilojoules. There's no way to do that directly in one step. So what we have to do instead is go from grams to moles, because if we know the mass of a substance, we know the mole value of a substance using molar mass. Once we have moles, we can now use our balanced chemical equation to go to kilojoules. So we can't do that top one anymore. So we'll first go from grams to moles, and then we'll go from moles to kilojoules. Okay, so let's start this problem. We're going to start with 75.0 grams of C6H12O6. And in order to go from grams to moles, we're going to have to divide by the molar mass. So 1 mole of C6H12O6 has a molar mass of 180.16 grams. Now, if you're unfamiliar on how to calculate molar mass, please go review that from General Chemistry 1. I have videos on my YouTube channel, but you could also look up in your previous notes. But this is something you need to be able to do independently and not with my help for calculating molar mass. That is something you should be able to do by now. So we take 75 and we divide it by 180.16 to get a mole value of 0.4162966. And that's going to be moles of C6H12O6. H12O6. So we've done our first part. We've gone from grams to moles. Now we want to go from moles to kilojoules. Well, here's where writing it out as is a little bit easier. So what we're going to do is take this delta H value, but instead of writing it per mole of reaction, we're going to say that this is 2,803 kilojoules per mole C6H12O6. Luckily, our coefficient out in front of glucose in our balanced reaction is 1. So, in order to cancel out our moles of C6H12O6, we'll put the 1 mole of C6H12O6 on the bottom and the 2,803 kilojoules on the top. Okay, so we just rewrote that delta H. Now, if we were talking about oxygen, then this would be over 6 moles of oxygen, or if we were talking about water, it would be 6 moles of water. Okay, it just depends on what you're trying to convert. Since we started with glucose and we converted to moles of glucose, I now have to use the moles of glucose to get the energy in kilojoules. So we'll take that 0.416 and we'll multiply it by that 2,803. And this is going to equal 1166.87. With sig figs, this comes out to 1.17 times 10 to the third kilojoules. So in order to produce 75 grams of glucose, we need to utilize 1.17 times 10 to the 3 kilojoules worth of energy in order to do that. So that's how much energy it would take to go through this reaction enough times. Okay, we're going through it multiple times, and then creating 75 grams of glucose. That's what that value, that delta H value, is telling us, the amount of energy that it's requiring to go through that reaction. Okay, let's try another one. I want you to try this one independently, and I give you some options for answers so you can check your work along the way. What mass of iron must be in a hot pack to provide negative 335 kilojoules of heat when the iron reacts with oxygen and is converted to iron 2 oxide according to the following thermochemical equation? So let's look at this problem. So we have negative 335 kilojoules of heat, and we want to know the mass of iron. So we want to somehow go from kilojoules to grams. This is just like our previous problem, but backwards. So we know we can't directly go between kilojoules and grams. There's no way to do that. So we have to go between moles along the way. So we're going to start with our kilojoules. We're going to convert that to moles, specifically moles of iron, because we want to get the mass of iron. Okay, so try this problem out, pause your video, do this calculation, and you have 4 options for answers to check your work. Okay, so in this problem, we're going to start with that negative 335 kilojoules of heat. And in order to go from kilojoules to moles, like we're asked to do here, we have to remember that this delta H of the total reaction is going to be negative 824.2 kilojoules per mole of reaction, which we know we can rewrite that as per mole, in this case of iron, because that's what we're looking for. The coefficient out in front of iron is 2, so we'll put the 2 right there, and that's what we'll use to do our conversion. So we start with kilojoules, and what we're going to do is we're going to use that delta H to convert to moles of iron. So we put that negative 824.2 kilojoules on the bottom so that kilojoules cancel, and we could put 2 moles of iron on top. So we see that kilojoules cancels, we're left with moles of iron. And we know that as we do this, let's see, negative 335 times 2 divided by negative 824.2, we get 0.8120909 moles of iron. We know that if we have a mole value of an element or a compound, anything that has a chemical formula, we can find the mass because we know molar mass allows us to convert from moles to grams or grams to moles. So we're going to utilize that, and we know that 1 mole of iron has a molar mass of 55.845 grams, because iron is on our periodic table, and that's where we find our molar mass. So we'll take that 0.8129, we'll multiply it by 55.845, and we get out 45.43 sig figs there, grams of iron. So our answer is A. So when we're looking at these thermochemical equations, we have some guidelines that we want to follow, some of which we already talked about. The first thing we want to make sure we follow is to always specify the physical state of our products and our reactants, because they are going to help determine the actual enthalpy changes when we go on and determine and learn about how to find that delta H value. So here's our combustion reaction of methane that we were talking about before. When we were going to carbon dioxide gas and water vapor, so water gas, that's when our delta H was negative 802.4 kilojoules per mole. But if our reaction instead yielded water as a liquid, that delta H value is going to be positive 890.4. So that's a big difference between those enthalpies. One's positive, one's negative. That's a big difference. Okay, so we want to make sure that we are denoting our physical states properly, so we account for them properly in their enthalpy changes. Okay, so always show your states: solid, liquid, gas, aqueous, etc. Our next guideline that we need to follow is that when multiplying an equation by a factor n, whatever that n value is, okay, we need to multiply the delta H value by that same factor. This is what we talked about previously about enthalpy being an extensive property. Okay, so we showed this with the water going from a liquid to a gas, and if we changed the number of moles, if we doubled it, we had to double the enthalpy. This is what this guideline is telling us to do. So we see this again here. We have our reaction with methane. I'm only using 1 mole of methane here, but then if I go to my second one, I multiply the entire equation by 2. I had to then multiply my enthalpy change by 2. Okay, so whatever I do to the equation, I also have to do to the enthalpy. Our final guideline is when we are reversing an equation, okay, that's going to change the sign, but not the magnitude of delta H, okay? So if we flip-flop where our reactants and our products are, then we just change the sign of delta H. So instead of having methane reacting with oxygen, creating CO2 and water, giving us a negative enthalpy, if I started with CO2 and water and wanted to create methane and oxygen gas, my enthalpy change for that new reversed reaction, so this one is reversed, my enthalpy change is still the same. It's still 802.4, but I've changed the sign to a positive. okay, because it's going to be the exact same amount of energy, just in the other direction. In this case, positive versus negative. So if you reverse an equation, you change the sign. You either go from a negative to a positive or a positive to a negative. You're essentially changing an endothermic reaction to an exothermic reaction, or an exothermic reaction to an endothermic reaction, in order to do the complete opposite. So let's practice using those guidelines and manipulating some of these equations to find their delta H values. So let's look. These come from your ALEKS homework, so you'll see a bunch of these on when you go to do those assignments. So what we want to do is we want to look at our initial equation here, which is up at the top, and for each of these reactions, we want to see what we're doing. Are we multiplying it by something? Are we dividing it by something? Are we flipping it? Are we reversing it? Are we reversing it and multiplying it by something? So we have to look at that. So let's look at where our reactants are. Let's see, I have an HNO3 and a magnesium on my reactant side, and an MgNO3 on my products, as well as hydrogen gas. So in each of these, let's look at where those end up. In our first reaction, my HNO3 and my magnesium are still on my reactant side. My magnesium nitrate and my hydrogen gas are still on my product side. So I didn't reverse the reaction, but my coefficients out in front are different. So I went from 2 to 4. I went from 1 to 2, 1 to 2, 1 to 2. So I multiplied the whole thing by a factor of 2. So what we have to do, that delta H, is also multiply it by 2. So we take that negative 443 and we multiply it by 2. Since I didn't reverse the reaction, I didn't flip it, okay, that sign is still going to be the same. So the delta H is just going to be negative 886 kilojoules. Okay, let's look at our next one. Here, I have magnesium nitrate and hydrogen gas on my reactant side, and my HNO3 and my magnesium on my product side. So that automatically tells me that I reversed. Okay, so that's going to change my sign of my delta H. So I'm automatically going to make that a positive. Now, did we change our coefficients? Well, my magnesium nitrate had a 1 and now it's a 3. Hydrogen's now a 3. Nitric acid is a 6 and magnesium is a 3. So I reversed this and I multiplied by 3. So we changed the sign of our delta H. So what you can do is think of that as you took that negative 443 and you multiplied it by negative 1. Okay, reversing it just multiplies it by negative 1. Okay, and then we multiplied the whole thing by 3. So this gives us a delta H of positive 1329 kilojoules. Finally, in our last one here, well, I have HNO3 and magnesium on my product side again, and I have magnesium nitrate and hydrogen gas on my reactant side. So that tells me that I reversed it. So automatically I know my sign of delta H is going to change. It's going to now be positive. Let's look at our coefficients. I have 1, 1, 2, and 1. So nothing happened besides that. So we just reversed it. So delta H is just going to be positive 443 kilojoules. Okay, let's do another one. Try this one independently. It's a similar problem. Okay, just a new reaction. So pause your video and determine what's being done to each of these reactions as it relates to the reaction at the beginning of the problem, and determine how delta H is going to change and what that delta H value is, just like we did in our last problem. So pause your video and go ahead and do that. Okay, let's stick with our highlighting method. I like doing the highlighting. It makes it easier for me to see everything. So we have P4Cl2 on our reactant side originally, and PCl3 on our product side originally. So our first reaction, we have PCl3 on the product side, Cl2 and P4 on the reactant side. So we didn't reverse it, but we changed our coefficient. So we went from a coefficient of 1 to a coefficient of 3. So we multiplied this by 3. So we're going to take that negative 1148, we're going to multiply it by 3 and get negative 3,444 kilojoules. Okay, our next one, we have P4 and Cl2 now on the product side and PCl3 on the reactant side. Our coefficients did not change, so we just change our sign, so this is reversed. So that just makes this a positive 1148 kilojoules. Okay, and then for the last one, we have PCl3 on the reactant side again, and P4 and Cl2 on the product side. Our coefficients did change by a factor of 2, so this was reversed and multiplied by 2. So we have a positive here. So we're going to take that 1148, which is now positive, we're going to multiply by 2 to get 2296 kilojoules. Now these two problems are a really great example of what you're going to see in your homework. You may also see something being divided by, so you could also have division. Okay, and I say division and fractions are also possible, so technically this could have been written as like 1/2 P4 solid plus 3 Cl2 gas goes to 2 PCl3 gas. Okay, thermochemical equations aren't dictated by if they have whole or fractional coefficients out in front. We can use fractional ones, which we'll see much more in our future lessons. So you could also have fractions, so you may also have to divide. So just keep that in mind as you go into your ALEX homework.